Hello, I'm Nan Jokerst at Duke University, and I'll be joined in this video by PhD student Corrine.
Hi, Nan.
In this video, Corrine will demonstrate the photolithography process, which we use to transfer patterns onto layers on a sample for feature sizes that range from roughly centimeters to microns.
I will go through the process steps for photolithography, and I'll demonstrate how to use photolithography to transfer a pattern to a silicon substrate.
The photolithography equipment is located in the clean room, so let's get gowned up and head into the clean room.
Before we begin, you may be wondering about the lighting in this room. Why does the light look amber in color? Well, the polymers used in photolithography are sensitive to shorter wavelength light, that is, blue light and ultraviolet light. These light-sensitive polymers are called photoresists, or simply resists for short. Short wavelength ultraviolet light, also called UV light, is used to expose photoresists during patterning, but we must avoid unwanted exposure from room light. So we use special lights that do not emit shorter wavelength light, and this light appears amber in color. That's why the lighting in this room appears different from typical room lighting. Let's get started with our photolithography process. First, we choose a substrate. In this case, we will be using a silicon wafer. Silicon is the most common semiconductor material used in the electronics industry. This particular wafer is 100 millimeters in diameter and approximately 500 micrometers thick. For this demonstration, we will pattern the wafer using photolithography, and then permanently transfer that pattern to the silicon using an etching technique. To pattern the silicon using photolithography, our first process step is to coat the wafer with photoresist using the spin coating technique. The photoresist is a temporary layer that we use to transfer our pattern onto the substrate. This is the spin coater we will be using. The spin coater has a small platform called a spin chuck that will hold our wafer. The spin chuck is hollow in the center, and a vacuum line provides suction that holds the wafer securely in place. We place the wafer on the spin chuck, taking care to get the wafer nicely centered. If the wafer is poorly centered, it will not spin smoothly and could result in an uneven photoresist film, or at worst, the wafer could fall off the spin chuck and get damaged during the high-speed spinning process. With the wafer centered, we turn on the vacuum to hold the wafer in place. We program the spin coater controller with the spin speed and time we wish to use. In this example, we will spin the wafer at 3000 RPM for 30 seconds. These values are typical for many photoresists. The recommended spin speed and time for a photoresist can be found in the datasheet for that particular resist. This information is often available on the product's website. We are now ready to spin the photoresist. We use a small plastic pipette to take a few milliliters of photoresist from the bottle. Next, we pipette the photoresist onto the wafer, right in the middle. It takes some practice to do this correctly. It's important to smoothly squeeze out most of the photoresist, leaving a small amount in the pipette. If you squeeze out 100% of the photoresist, you will create small bubbles in the photoresist on the wafer, which can cause non-uniformities in the film during the spinning process. With the photoresist on the substrate, we press Start on the controller to begin the spinning process. The wafer quickly spins to 3000 RPM. It will spin for 30 seconds as we programmed it, then slow to a stop. After spinning the photoresist, we remove the wafer from the spin coater and bake the wafer on a hot plate at 115 degrees Celsius for 1 minute. The bake time and temperature can vary depending on the photoresist being used. The bake removes any remaining solvent from the liquid resist and solidifies it into a solid thin polymer film. This particular resist forms a polymer film that is 1.5 micrometers thick. For comparison, the width of a human hair is about 100 micrometers. So this film is quite thin. After the 1 minute bake, we are now ready to pattern the wafer. To pattern the wafer, we use a photolithography tool. This tool holds the wafer in place, aligns and contacts the photomask to the wafer, and illuminates the photomask and substrate with ultraviolet light. Let's go through these steps now. First, we program the desired exposure time into the instrument. Different processes require different exposure times. The exposure time is the amount of time we will illuminate the wafer with UV light. For this example, we will use 11.5 seconds. Next, we put our photomask into the instrument. The photomask contains the pattern we wish to transfer to our substrate. Here, we see the pattern on the photomask, and looking under a microscope, we can see the pattern more clearly. We place the photomask on the plate. Small holes in the plate lead to a vacuum line that provides suction to firmly hold the photomask in place. We then carefully take the plate and slide it into the instrument. The plate locks into place. We take our wafer that is coated with photoresist and place it onto the wafer platform. Again, vacuum suction holds the wafer in place. We slide the platform into place. With the photomask installed and the wafer in place, we are ready to start the exposure process. We will start the process by pressing exposure on the instrument. At this point, the instrument automatically raises the wafer so that it gently makes contact with the photomask. The UV light source will then illuminate the wafer for the programmed amount of time, 11.5 seconds for this example. You'll notice the color of the light source. It appears purple or violet, and there is UV light that you cannot see. It is the UV light that is important for photoresist exposure, and the lamp is carefully calibrated so that a precise amount of UV light is emitted during exposure. Now that exposure is complete, we remove the wafer. Our wafer is now referred to as exposed. We are now ready for the next step, which is developing the photoresist. To make the photoresist show the pattern on the substrate, we develop the photoresist wafer using a chemical called developer. We pour developer into a dish. The developer for any particular photoresist is suggested by the photoresist vendor. The important point to remember for this photoresist is that the developer will selectively dissolve away the portions of the photoresist that were exposed to UV light. This is called positive photoresist. Some photoresists, called negative photoresists, behave in the opposite manner. The UV exposed areas are the areas that are not removed by the developer. Let's continue with our positive photoresist process now. We place the wafer in the developer. The development process takes 60 seconds. Slight agitation during development will ensure a uniform process. After 60 seconds, we remove the wafer and rinse with deionized water, then blow dry with compressed nitrogen. We have successfully performed photolithography. Let's take a look at our patterned wafer under the microscope. We will now inspect the wafer to ensure we have produced a quality pattern. Great! We have a nice pattern. The photoresist looks just like the pattern on the photomask. Now, we will transfer that pattern into the silicon using a silicon etch. The silicon that is not covered with photoresist will be etched. The silicon covered with photoresist will be protected and thus not be etched. The etching process is performed using a separate dedicated instrument called a reactive ion etcher. The entire process takes about 30 minutes and won't be shown in this video. Here's the etch sample. The silicon has been etched in the areas that were not protected by the photoresist. Let's remove the photoresist using an acetone solvent. Now, we can see that we have a copy of our photomask on the silicon wafer. Several microns of silicon have been etched away. We cannot see the depth of the etch clearly using an optical microscope, so we can use a scanning electron microscope to get a better look. Here, we can see the mask pattern has been transferred to the wafer, and we can measure how deep the pattern was etched into the silicon. Thanks for joining me today to learn about photolithography.